Hello, so in this video we are going to look at a task about Maclaurin series. We have a function, strangely enough e to the power of x minus 1, and we're asked to prove that the start of the Maclaurin expansion of this is 1 plus x squared plus 5 over 6 x cubed and so on. And the fact that we're given only these four first terms will be significant in this. So I will start by doing some expansion of e to the power of x, just so we remember it. And we know that e to the power of x equals 1 plus x plus 1 half x squared plus 1 over 6x cubed plus and so on. And it's going to turn out we don't need more terms. Next, I'm going to introduce a substitution t, and I will put that equal to e to the power of x minus 1. So t is the exponent in the function I'm after. And obviously if you subtract 1 from what we have up here, it turns into just x plus 1 half x squared plus 1 over 6 x cubed and so on. So that's okay then, and we can see that our function that we are interested in we can Maclaurin expand it in terms of t. So e to the power of t is what we're after, and is therefore, of course, t mod 1 plus t plus 1 half t squared plus 1 over 6 t cubed and so on. And we need to put this somehow in terms of x. So that would be okay if we knew what t and t squared and t cubed and so on, what they were. But t is an infinite series, so how do we do that? Well, we're only interested in x terms up to power of 3. So basically everything that will produce anything larger than that we can throw away. So in the following I'm going to expand t and t squared and t cubed and so on, but only up to terms of x cubed. Anything higher than that we will disregard. And if we wanted a nicer pattern, we could have seen a pattern possibly. Now we just asked for the first four terms, so that's what we're going to do. So let me again just write that t equals then x plus x squared over 2 plus x cubed over 6 plus, I'm not going to go on because I'm not interested in anything of higher order than 3. What is t squared? Well, I could imagine this. I could do the multiplication of t by itself as an ordinary polynomial expansion, and I'm ignoring again everything that gives me more an x term higher than order 3. So I'll have, starting with x times all the terms, x times itself is x times 1 half x squared is, x times itself is of course x squared. X times 1 half x squared is 1 half x cubed. X times x cubed over 6 is x4 over 6, which I'm not interested in. Next I need to then take this term times every term, so 1/2 x squared times x is going to be 1/2 x cubed. This term times itself will be an x4 term, and I'll ignore that. And so on. And I see that taking this term times anything of higher order will give me x4 or higher, so I ignore that. This term, the x cubed term, can't be multiplied by any of the other terms without giving too high order, so I'll stop there. What is t3 then? Well, it's t times t squared. So I'll start by the first term of t and multiply it. X times x squared is x cubed. X times this term will be of too high order. So already now I can actually stop, because I can't do any other multiplication without getting a term x4 or higher order. X times this will be x4, x5, and so on. And this term, the second term in t, is no use even starting, because the first term I would multiply it with would give me an x4 term. So t3 is x3 plus higher order terms. Do I need a t4 term? Well, no, because the lowest order x term in t4 would be x4, and I'm not going to use that. So all the other terms will be ignored. Looking here, we see that we are interested in t, but in t squared divided by 2, and in t3 divided by 6, and so on. And I'm actually going to make a table of those, because I want to match it term by term later. So even if it seems like unnecessarily much writing, let me just scribble down again that t equals x plus 1/2 x squared plus 1/6 x cubed, and so on. T squared divided by 2, which is what I'm after, is going to be x squared divided by 2 plus, I have actually two similar terms, x cubed divided by 2 plus x cubed divided by 2. So the total x cubed term in t squared will have a coefficient of 1. That is to say, it will be simply x cubed. But here I'm dividing it by 2, so in the final version I'll get x cubed divided by 2, and ignoring higher order terms. And t3, the t3 term, is supposed to be divided by 6, and it's just then x cubed divided 6, and higher order terms. I'm running out of space. So if we move that up a bit. So now finally I can do my expansion, because what I'm after is this. So e to the power of t equals 1 plus t squared over 2 plus t3 over 6, and higher order terms, which equals 2 . There's only one constant term in all these three, so it's going to be a 1 plus. There's only one x term in all these three, so I'll use that. Where will I get x2 from? Well, I have 1/2 x squared term there and 1/2 x squared term there. So let's do it this way. The coefficient of x squared will be 1/2 from t and 1/2 from t squared halved. There's no x squared term in t cubed and not in any of the ignored higher order terms. What about x cubed? Well, I will get 1/6 from t, 1/2 from the t squared over 2 term, and 1/6 from the t cubed over 6 term. So I don't know if you can see very well like this. So here I've taken the powers of x in increasing order, 0, 1, 2, 3, and so on, and collected terms from the t series, the t squared over 2 series, the t cubed over 6 series, and so on. And if I simplify this, I get e to the power of t, which is same as e to the power of x minus 1, equals 1 plus x plus, that's just 1, x2 plus 1/6 plus 3/6 plus one of them is 5/6 x cubed plus various higher order terms, which is what we were asked to actually prove, which makes us very pleased. We could have gone on and done the x4 and x5 terms, and so on, of course. It would have been increasingly difficult, not theoretically, but in terms of lots of different terms to keep track on. So if this turns up on an exam or similar, you see how beneficial it is to be really systematic about it. This was not the first attempt of solving it, obviously, so the further you go, the more you see that, oh, I can systemize it in this way. Let's review what we actually did. We expanded e to the power of x, we introduced t, and expanded e to the power of t. And then we tried to figure out what is then t, t squared, and t cubed. And we got those by consistently ignoring anything of higher order than 3 when it comes to x. So we had first the t expansion, multiplying that by itself and ignoring everything higher order than 3, we got the t2, t squared. Doing the same with t cubed and so on. And if we had wanted higher order powers of x than 3, this list would have gone on and we would have needed to have the t to the power of 4 term as well. We adjusted those series for the coefficient we're going to use for t, t squared, and t cubed. And finally, we collected the various powers of x from the different t expansions and simplified and answered. Try it for yourself. It's not as messy as it might seem, but you need lots of space, lots of paper, and you need to be systematic. Good luck!